In the last video, we came up with our equations for N1, N0, and S. And I worked on the first K-map for N1 to simplify the equation. So here's the K-map that goes with that. And as you can see, I plotted the don't cares. And the don't cares, if you recall, you can interpret as a 0 or 1, whichever works to your advantage. In this case, a 1 works to our advantage, so we can create these two groups of 2. So here's your simplified equation. Now, if I just scroll down, in the case of N0, I've plotted our don't cares as well. And as you can see, in the first one, the blue circle here, it works to our advantage to have a 1 here. Let's see if I can get in there and change this to a 1. But in the case of this one here, this X, in the red circle, we don't need the red circle. The red circle will create another term. So I will interpret this one as a 0 and remove this circle. Right? So that gets rid of one of the terms for us. So we just have this, which is a 2-variable term, and then this one by itself, we can't group with anything, creates a 3-variable term. All right, and then finally, our equation for S, the X's work great. They work to our advantage in a huge way here. You can see it creates 2 groups of 4. I've got the blue circle here for this cluster and then this red circle here. So interpret these as a 1, and what that does for us is create 2 terms, 1 variable each. So now that we have our simplified equations, I want to show you one thing from your book before we start drawing our circuit. So take a look at the circuit that you have here in this example in your book. The circuit is for the combinational logic. The present state values go into the circuit, and your output is this external output Y and your next state. Okay, and they're going into this register here. So you have 2 bits going into your register. And as we saw in a previous section in your book, your register is made up of what? It is made up of 2 flip-flops, 1 bit each. So since you have a 2-bit encoding for each of your states, you need 2 flip-flops. So when you get over to Cedar Logic, you'll see that if you go over to your registers section, the smallest you have is a 4-bit, which is not what we have going on here. We have 2 bits. So you're going to need to use flip-flops to draw this circuit. So I'm going to do that first. And we're going to use a D flip-flop. A D flip-flop has 1 input and 1 output. So let's bring this over. And again, you're going to need 1 flip-flop each for a bit. If you right-click on these, it'll flip them on their side, which will be a little easier to work with. I'm going to lower this further. Okay, and as you can see, I already took the first step of bringing in our equations so that we don't have to toggle back and forth. And I know this is really weird, but an apostrophe doesn't appear, so I had to use a little caret top. Now, I have no idea why the apostrophe character does not appear when the caret top does. Whatever. Anyway, so just bear with me. This caret top represents the complement of P0 in this particular example. All right, and so when you look at your flip-flops down here, here's your input D, and here's your clock. Here are your outputs Q and the complement of Q. So when we start to connect, let's start with N1. You know you have an AND here, an OR, and another AND, and an inverter. So bring in all of those gates. So 2 ANDs, an OR, and an inverter. Okay, I also need a toggle for A, and I need to start labeling everything. So here's my A. I want to label this as my P1, this as my N1, this as my P0, and this is my N0. So I'm going to go over to decorations and bring in text. And I'm going to pause the video here so you don't have to watch me make all these changes, okay? Okay, so I have everything labeled here. As I said, this is your present state coming out of the flip-flop, your next state going into the flip-flop. I've got P1 and P0, two different flip-flops, your external input, and I started connecting, but I wanted to finish up with you guys. So here I have P0A, and so that's where I started here. So now we want to connect this guy. It's going to come out a little messy, but we'll do our best to make this nice and neat. Okay, so there is P0A, P1 and the inversion of A. So P1 is right there. We'll see how best to organize this after. Okay, and then I've ORed them together, and since this is N1, right, so we have to connect to N1. Ooh, that looks great, right? Okay, I'm just going to put it way out here. The next one's N0 and S, and I'm going to go ahead and build those. So I'm going to pause the video, build them, and then come back again. So this is my completed circuit, and I labeled my N1, my N0, and S here. And just as a note, you can see I used P1 as this output line, and then the complement of P1 is the second line. So I did the same thing here with P0. Now the next thing you need, and this is kind of what I wanted to highlight for going forward for you when you're using flip-flops, is you're going to need the clock, so a pulse, to change the inputs, and you need what's called this low active reset. So connect your clocks here to the triangles on each flip-flop, and your low active reset gets connected here. So you're going to need to connect each one. And the low active reset, what that does for you is it resets the input values back to 0. And you need to do that in order to be able to test. See if I can make this read. So now you can see your clock pulsing. There it goes red. That means it's on. Turn on your low active reset. And change your input A. Okay, and you can see that N0 is a 1, comes in, changes the result of P0, changes the result of N1. So you can play around with it and turn this off, reset everybody to 0 for your flip-flops, and you can see the difference. Okay, so you can go ahead and play around and see the different values. And I've posted this document as well as the Word document that goes with it on Blackboard.